And he's been involved in the early works of dynamo theory in the 60s, also in predictions for the dynamo experiments with the sodium and also radar. And today we'll give an overview of Thank you.
Okay, thank you very much. I understood the invitation to the seminar so that I should give an elementary introduction, not necessarily for the participants of the program, but for a wider audience to dynamo theory. In that sense, I will say a few words about observational facts on magnetic fields. I will explain the idea of the self-exciting dynamo and some elements of dynamo theory, and in particular the mean field concept in dynamo theory. And if there is some time, I will speak about the dynamo experiments. The longest known magnetic field, cosmic magnetic field, is that of the Earth. The Earth is a cosmic body, and evidence for this field, or at least for a compass which works with this field, is very old, 3,000 years ago in Mexico, 2,000 years ago in China, and there are already other old books about the magnetic field in general of the Earth. So, for example, the concept of polarity, North and South Pole, was introduced already by Pericles in the 13th century, and there's a very important work by William Gilbert. He already knew about the global structure of the magnetic field of the Earth. The central sentence is, the Earth is a big lodestone. Later, not much later, the westward drift of the magnetic field, the declination of the magnetic field was discovered, and at the beginning of the last century we learned about reversals, polarity reversals of the magnetic field. So far about the Earth's magnetic field. In 1908, Hale discovered strong magnetic field in sunspots by analyzing the spectra. There were line splittings in the spectra, which are, as we believe, caused by the Zeeman effect, and he concluded that there are also strong magnetic fields, strong compared with the magnetic field of the Earth, factor 10 to 3 or 10 to 4. In sunspots, you know that the sunspot phenomenon is a periodic phenomenon with a period of 11, or if you consider the magnetic polarity, of 22 years. In addition to the fields of sunspots, there is a general, much weaker magnetic field. In the time after the Second World War, a lot of magnetic fields on other objects was discovered. So magnetic fields at some main sequence stars of type A, again 10 to 3 times the magnetic field of the Earth. It was discovered by spectroscopy, by Zeeman effect. Spacecraft missions brought us knowledge about the magnetic fields at planets of the solar system. There were also strong magnetic, now really also strong magnetic field tended to Tesla at some white dwarfs. Magnetic cycles like this solar cycle were discovered at sun-like stars. Magnetic fields, radio astronomers discovered magnetic fields which penetrate the galaxies and also intergalactic space rather weak, but very large scales in space. And we have extremely strong magnetic fields, extremely weak, extremely strong magnetic fields, and neutron stars first concluded from other observations, not magnetic observations, but in some cases also shown, confirmed by direct observations of magnetic fields. There were, from the very beginning, discussions what could be the causes of all these magnetic fields. You can think in the case of the Earth of the paramagnetic core, but you have to rule out this because even our cool Earth, with about 6,000 degrees inside, is too hot to have paramagnetism. The Curie temperatures which limits the existence of paramagnetism are 1,000 or less than 1,000 degrees for all known materials. You can think of thermoelectric effects. You have temperature differences and chemical differences, and then this should drive currents. Think of other such things, different inertial behavior of electrons and ions, and so. But all these ideas have to be excluded, at least for bodies like Earth or Sun, because if they at all give magnetic fields, they give much too weak magnetic fields. The only idea which was proposed and which survived was the idea first mentioned in a two-page paper by Larmor in 1990, that the magnetic fields, he thought of the Sun, magnetic fields of the sunspots are due to electric currents which are generated just after the pattern of a self-exciting dynamo, which was known from general physics and from engineering at this time. It was known since the middle of the 19th century. These people, for example, Werner von Siemens, took induction machine which produces, if you turn the anchor in a magnetic field of a permanent magnet, which produces an electromotive force which could drive a current. You can replace, or he replaced the permanent magnet by an electromagnet and had it just by this current. If you then have an initial weak field, say by the remnants of the core material, then you get first, when you rotate the anchor, a small electromotive force, and quick amplify, the arrangement is correct, the original small field, and then in the next step could amplify it more, and so on. To understand this principle, it is reasonable to consider this arrangement, a disk dynamo, a metallic disk which rotates around an axis. If you have some magnetic field, then a voltage difference between the axis and the rim of this disk occurs, and you can connect, applying contacts, the rim with the axis, with a wire, and you can wind the wire in this way that you just reproduce the assumed original magnetic field. If you want, you can write down the Kirchhoff rules. Oh, consider a circuit which is given by these wires and by the connection through the disk. You can describe it inductivity and resistance, and then the voltage at the inductivity, the voltage at the resistance, sum, is equal to the temporal change of the flux through the disk. And so you write down this equation. This is a magnetic flux, omega is the rotational rate, and you can relate the flux to the current via another induction coefficient, and then you have this simple differential equation which you can immediately solve. Omega star is a modified angular velocity, and you see if the resistance is large, then you have a decay. If the resistance is smaller than this omega asterisk, the current, so the magnetic field, can grow. You have dynamos. This is the idea of the self-excited dynamo. But if we consider the Earth or the Sun or other conducting bodies, we have no isolated wires. We have to write down Maxwell equations and completing constitutive equations for this material. So we do it usually in the MHD approximation, which means firstly it is a quasi-steady approximation as used in ordinary electrodynamics, where the displacement current in the Maxwell equations is ignored. That means we exclude electromagnetic waves, and we assume non-relativistic motions, so that the Ohm's law takes this simple form. You can derive from this induction equation, take Faraday's law and replace E by what you get from Ohm's law, and so you arrive at this equation, which we call induction equation, and eta is called magnetic differentiality. If you have solved this equation with a given U for a certain problem, then you can calculate all other quantities of interest and calculate K and J and so on, without another integration. So this equation is the basis of the kinematic dynamo theory. The magnetic field dynamo has to satisfy this, this induction equation inside the fluid body, and you have to add initial and boundary conditions, and you will get a solution. Okay, if there is no velocity, you can easily show that E must decay. That means for a dynamo, the term with U cross B must have a certain value, and you can estimate the ratio between this U cross B term and the diffuses term is eta with this dimensionless magnetic Reynolds number. You understand, we define a dynamo just by saying the magnetic field shouldn't decay in the course of time, and so a necessary condition, necessary, not sufficient condition for a dynamo is just that the magnetic Reynolds number is above a certain critical value, which is, roughly speaking, in the order of unity. In practical cases, this is more than 10. Okay. To explain it a bit more in detail, consider the case where U is independent of time, and make this ansatz. here separation of space and time dependence, then the reduction equation turns into this equation which no longer depends on time. And this equation, together with the boundary conditions, defines an eigenvalue problem. The eigensolutions depend, of course, on the magnetic Reynolds number that is hidden here. In general, the eigenvalues P are complex, and we can split it into a real and imaginary part. And we have a dynamo if at least one of these lambdas is non-negative, since it depends on Rm. This defines a critical magnetic Reynolds number for a dynamo. You can take the sum of all these expressions with all eigensolutions and the equation. So the solution of the original induction equation is like this. In most cases, the pi constitute a complete system of functions, and then you can represent an arbitrary initial condition in this way, put t equal to 0, and if the sum b can represent initial conditions, this is a general solution of the problem.
Excuse me.
Yeah.
Yeah. That eigenvalue problem is only valid in Cartesian coordinates, right? The way you wrote.
I formulated here independent of coordinates.
No, but the way you wrote is just on Cartesian coordinates. Otherwise, there is an extra
I
term
wrote the
there.
vector
Yeah,
differential equation.
there is an extra term there.
Sorry?
There is extra terms if you consider the curvilinear coordinates.
No. If you specify it to a special coordinate system, you have all the special terms, but say express the curvature of but if you understand the equation I gave here as a real vector equation, then we have no extra terms.
If it is curvilinear coordinates, the derivative of the basis has to be taken into account, so that it will generate curvature term.
Maybe we can discuss it as well later. Sorry. Yeah. Many attempts were made to find, to assume velocity fields and to derive solutions of these equations, or which have something to do with, say, the situation in the Earth or in the Sun, but all these attempts failed. And the first exact result which was derived was of negative nature. Cowling showed that there is no dynamo with an axisymmetric magnetic field. It doesn't only mean that, say, in the case of the Earth or the Sun, the field cannot be symmetric with respect to the rotational axis. But if you find for a given magnetic field any axis with respect to which the magnetic field is symmetric, then you can exclude this field from dynamo. There's another theorem which was proved, and there are several more. And remember that the idea of the self-excited dynamo, cosmic case, originates from 1919, and it was only 58 when Herzenberg, at this time in Copenhagen, gave the first existence proof of the dynamo. The existence of a technical dynamo with isolated wires is no argument for the existence of dynamos which we have in mind here, which we often call homogeneous dynamos because we have no isolating materials. So, Herzenberg considered a conducting sphere which is at rest, or the interior of which is at rest, except in two spherical regions which rotate like rigid bodies, about axes which are given here, and if these rotation rates are sufficiently high and there is a special arrangement of the axis in space, then indeed non-decaying magnetic fields are possible. It was really interesting as an existence proof for the dynamo, but of course it has nothing to do with motions as we assume in the Earth or in the Sun or so. Another simple example was given by Roberts. It is a flow pattern which depends only on x and y and not on z, and it consists of, it is periodic in x and y, of motions like this in this plane, and motions into the plane here, or out of the plane here. This pattern, the velocity of this pattern is able to maintain a magnetic field, which then, however, must, by dynamo theories, depend on z. The flow doesn't depend on z, but the magnetic field must depend on z. Another example, and 1 year later, was given by Ponomarenko. He considered again an infinite space filled with conducting matter at rest, except in an infinite cylinder which moves in this way, in axial direction, and it rotates. It has contact, electrical contact to its surrounding, and then we found that there are waves traveling in this direction, which don't decay. Okay. After that, and with the progress of computer technique, many solutions were calculated. So, for example, in spherical bodies surrounded by free space, there's a catalogue of simple flow patterns which produce magnetic fields, but it was not close to what we expect in real cosmic bodies. And the approach which proved to be very useful was the mean field dynamo theory. It's just made for situations in which complex flow patterns exist, so convection in the Earth or in the Sun, or even turbulent motions. The idea is to split both velocity field and the magnetic field into mean parts and fluctuating parts. And the mean parts are defined by some averaging. You can average in space or in time, or statistical averaging is not important. Important is only that the averaging procedure satisfies the Reynolds rules. I will come to this. Then, subjecting the induction equation to averaging, you find the same equation for the mean fields, with one exception. Here is an additional electromotive force, which is defined by the cross product of the fluctuations u and v. That's what I showed you on the slide before. If you have helical fluctuating motions, as you have it at rotating bodies, this quantity has a path which is parallel or antiparallel to the magnetic field. It means a path like this. This changes the character of this equation. The u bar plus b bar has no component in heat population. Now, a contribution to this occurs, which is parallel to B. Then, for example, the proof of Coulomb theorem takes down. You can have axisymmetric magnetic fields as a solution of this equation. The deviation from axisymmetry is then hidden in these fluctuations. This alpha effect allows mean field models which indeed reflect essential features of cosmic magnetic field dynamos in cosmic field. Again, a bit more in detail, start with the Maxwell's equations and Ohm's law, from which you can derive the induction equation. Assume that you have an averaging procedure which satisfies these Reynolds averaging rules known from the usual theory of turbulence. So it is distributive. The average of a space derivative is equal to the derivative of the average field, and the same with time. Twice averaging is the same as simple averaging, that means fluctuations. Average vanish, and you have this relation. And then you see, as follows from this, if you have two quantities, f and t, which are both fluctuating, and you take the average, then the result is not only the product of the mean parts, but you have in addition this term. And this is just the reason for this term. If you subject this to averaging, you have this, and just as a consequence of what I explained here, we have this electromagnetic force. We have to study this mean electromotive force U plus V average. And if you take the original induction equation and the average induction equation and make the difference, then you see that the quantity B, which occurs here, we consider U as given, has to follow this equation. This U plus B dash is just the abbreviation for the fluctuations of U plus B. So you conclude from this equation that B is a function of U bar and B, and it is linear in B bar. If you multiply this by a factor of 2, so the solution B goes, of course, also with a factor. So the same applies for the electromotive force. That means you can write this electromotive force in this form. This is a term independent of B, and this is the term which depends on B. And in the sense, functions of U bar, it is linear. Then, even without making calculations, you can say that this term can be represented in this way. This is linear, and you can this kernel, which depends also on the integration variables xi and tau, considers B in all space. But if you think of a turbulent situation, then the correlation between two quantities at different points in space and time is only markedly different from zero if these 2 points are not too far from each other. So the distance is not much larger than correlation length and correlation time. And that means that this kernel K is not markedly different from zero for larger psi. If it is so, then you can, this is the same what I had on the slide before, then you can expand this into a Taylor series, and here are only the two first terms, and if you insert it here, you see you can write the electromotive force. It's this way. You have a term which is B without derivatives, a term is first spatial derivative. This means you can have also time derivatives and higher spatial derivatives. You must decide, depending on the problem, what here really is. So, okay, that's what derived, and consider a simple example. Assumes there is no mean motion, and U is a homogeneous isotropic turbulence. I understand homogeneity in the sense that any average quantity is invariant under a translation of the I understand isotropy in the sense that any average quantity is invariant on the rotation of the field about an axis, any axis. I define here also another property. It's a neural symmetry or reflectional symmetry. You can reflect U at a plane or at a point. And then the question is, does it change mean quantities? And if it doesn't do so, I speak of a neurosymmetric or non-helical turbulence. Otherwise, yeah, that will be. Okay, homogeneity and isotropy means that these coefficients, like homogeneity, are independent on the space coordinates. Isotropy means they can only be isotropic tensors, delta and the epsilon tensor. And if you, in the case of isotropic turbulence, you cannot define a vector vector turbulence, and so you have all this equal to 0, and you find simply that your electromotive force must have this structure. Alpha times B means beta times curl B. Curl B is the current K bar. So, and if you put this in Ohm's law, you find this simple form of Ohm's law. Here is no longer the conductivity sigma, but a modified conductivity sigma, which contains this beta, and which can be quite different from the original conductivity of the matter. So, in the case of the sun, for example, the difference between this and this is a factor 10 to 4, which is of some interest if you estimate the lifetime of sunspots also. So, and you can also show that alpha is equal to 0 if you have neurosymmetry, or if your turbulence is non-helical. Okay. No, this one. Again, this example we consider. You can insert the expression for E into the induction equation, and then you get this. And if you make this answer with a simple exercise to calculate the P, you find this. That means for sufficiently high values of alpha, so that this term so comes this term, you have growing solutions. You have the dynamic. Of course, the homogeneous isotropic turbulence is an academic example. You may have it under certain conditions in the laboratory. Oh no, let me say, homogeneous isotropic but not neurosymmetric turbulence, so that alpha is unequal to 0. is an academic example. But if you go to rotating bodies, so that the turbulence is subject to the influence of the Coriolis force, then the situation is different. You determine the Coriolis force just by a right hand or left hand rule. So that you see that the Coriolis force introduces some violation of the mirror symmetry. And if you calculate the electromotive force now for an inhomogeneous turbulence, say inhomogeneous by a gradient of the turbulence, it's then 0, or by another influence, and in a rotating body where you have angular velocity, you find instead of simply alpha times v, you find this expression. You have again a contribution which is parallel, antiparallel, depending on the sign, to the mean magnetic field, but you have a few more expressions. The alpha effect, in that sense, causes an interplay between colloidal and toroidal fields. Colloidal fields, in the axisymmetric case, which I only consider here, are defined such that they are in meridional planes, this, and toroidal fields are perpendicular to this, something like this. Okay. The alpha effect changes sign from north to south hemisphere as a consequence of this. The product which changes sign if we go from north to south hemisphere, so it's radial direction, that is always an axial direction, so that's why it changes the sign. So, and if you have here a magnetic field in this direction, the positive part, you must have also a current in this direction. And here in the south hemisphere, alpha has the opposite sign. That means you have also a current in this direction, here against the magnetic field. And such currents just produce the polarized field which I have shown. The alpha effect with the polarized field, the currents cannot completely follow the field lines because you have no production space. What you get are current systems like this and here like this, just current systems which reproduce these magnetic fields. And this is the idea of the so-called alpha square dynamo, alpha square because alpha acts twice, with the toroidal field and the polarized field. So this is the idea of the alpha square dynamo. I didn't speak about this. If you have a differential rotation, because that's angular velocity varies with r, then this could support the generation of the toroidal field. Here, assume here that say the inner parts rotate in this way, the outer parts are at rest, and start with originally or with the original polarized field line. Then this motion winds up the field lines, and you have after some time a picture like this, where the field lines or the orientation of the field is here this way, and in the south hemisphere this way. So it means differential rotation is able to produce from a polarized field a toroidal field. You can analyze this as a sum of a polarized and a toroidal field. Here you can also have a production of the toroidal field by differential rotation. And if this process dominates, if the differential rotation is sufficiently strong, you get a dynamo which we label as alpha commutator dynamo. And this is widely elaborated in the future to cosmic objects. I give only one very old example. I should say that the alpha omega dynamo can have solutions which behave monotonically in time and also oscillatory solutions. By the way, the alpha dynamo is the first model which was the model which was proposed for the Sun was an alpha omega dynamo with oscillatory solutions, and in this very old paper the solutions were computed numerically, and the butterfly diagram, the distribution of the sunspots in the latitude, in the dependence of time, was reproduced in this way. So in between, these models are much more elaborated, and such models are discussed also in the program. I will not go into detail. So far, I have not spoken about the back reaction of the magnetic field on the fluid motion. And this is, of course, a very important process, which, by the way, also limits the growth, the exponential growth of the dynamo fields. And if you want to consider this, you have, in addition to the induction equation, also write down the momentum balance, the Navier-Stokes equation, including the Lorentz force J equals speed. And here, with a view to the pure dynamo, buoyancy term is added, which depends on the deviation of the temperature from equilibrium contribution, and I have to add also these consequences. These equations are much more complex than the induction alone. You can formulate them in a dimensionless way, and you have then, in this case, 4 dimensionless parameters, the Ekman number, which is the ratio of the diffusion term, the viscosity term, the Coriolis term, the radler number, which is responsible for the onset of development of the convection, the Prandtl number, and the magnetic Prandtl number. Unfortunately, these quantities have very extreme values, which makes the calculations, the numeric calculations, very difficult. And so the Ekman number 10 is 15. 10 to minus 15, and the magnetic one now 10 to minus 6, and no numerical simulation has been done so far with these extreme values. One remark, the ratio of the Reynolds, the fluid Reynolds number, the magnetic Reynolds number, is just given by the magnetic Prandtl number. And if the magnetic Prandtl number is small, the Reynolds, fluid Reynolds number is much higher than the magnetic Reynolds number. And if the magnetic Reynolds number is, say, 100, then the fluid Reynolds number is much higher. That means you have no longer laminar motions, you are in a region where you have high diffraction motions. This makes the situation even more complex. I think you all know this picture. This oil. What is this? Oil. This was a calculation on the basis of equations as I showed you before, but with parameters which are far away from realistic parameters for the Earth. Okay. You can the mean field concept, as I explained it to you before, also to the momentum equation. So this is the usual momentum equation, and if you subject it to averaging, you have the gains original form for the mean fields, but in addition a conformative force which is defined in this way. It contains the action. Oh, look at this. You can represent it as a tensor divergence of a pressure tensor, and it contains radlers, which are known to see with turbulence, and in addition a tensor which contains the maximum stresses. At the moment, such things were elaborated more in detail. You can extend this. Okay. So far about the theory. It's always good to look at experiments which support or don't support the theory. Look at this. It is but in addition, the interplay between theory and experiment always pushes the understanding of the situation. And in particular, in view of the very complex back reaction of the magnetic field on the fluid motions, you cannot be sure that you cover it by theoretical investigations, and it is good to have the comparison with experimental data. You know that the magnetic Reynolds number must be large for a dynamo, and how to make it sufficiently large. So you should have metallic conductivities, and the material should be, you could think of mercury, for example, but the electric conductivity of mercury is rather small, and it is hard to reach sufficiently large magnetic waves. The material which was used in most of the experiments, I think all experiments which I report here, is liquid sodium. Liquid sodium, or sodium is liquid after 100 degrees centigrade, and it has then an eta of 0.1 meter square per second. And if you take, for example, a velocity of 1 meter per second and characteristic length of 1 meter, then you find magnetic Reynolds number of 10. It is already very much considered that you have a flow of 1 meter per second through a cross section of 1 square meter, like this. This would mean you have 1 cubic meter per second. You need very huge pumps to come to this, and 10 is not enough for a dynamo. So, the first, you can also think of fluids for which the magnetic permeability is bigger than the permeability of bismuth. And I mentioned this Herzenberg proposal, and experiment was made also early following this pattern, but not with spheres, but with cylinders, which rotate, and there it was not an experiment with fluids, it was a rigid metal block here in which these cylinders rotated, and the metal had a relative permeability of between 150 and 250 in this way. The magnetic Reynolds number was enlarged. Indeed, some dynamo effect was reached. In another case, depending on the special arrangement, oscillatory dynamo. Nothing happened with copper, with the relative permeability to 1. And again, okay, I will not go into the details. Interpretation of these results is also complex because permeable materials have nonlinear behavior, hysteresis phenomena, and so on. That is why it is very hard to interpret, apart from the fact that it is not a dynamo with a fluid. Another experiment which I want to mention is not really a dynamo experiment, but an experiment which should prove the existence of our effect. These are two channels, braided channels through which liquid sodium is pumped, and the arrangement of the flow pattern is so that an alpha effect should occur if you apply an external magnetic field in this direction by coil, then a voltage difference should occur between here and here. Here, this is the coil. This experiment was carried out in Riga, so it's an experimental device, and you see here this is the voltage measured with different external magnetic fields, independent of the flow velocity square. In this way, it was shown that the alpha effect really exists in this experiment. There was the second. It was no dynamic experiment. It was only an experiment to demonstrate the existence of the alpha. Another dynamic experiment was carried out, prepared, and later carried out in Riga with the Ponomarenko flow, which I will explain to you. The Ponomarenko flow was chosen because the magnetic Reynolds number, the critical magnetic Reynolds number, was the lowest among all possibilities which existed at this time. It was about 80. You see, it was about 10, which I mentioned before. And the first experiment with this, I should mention, I said you have here waves, magnetic waves, which travel in this direction. So our colleagues added a backflow to this, and here a backflow which produces standing waves. And the first experiment was prepared in Riga but done in what was Leningrad at this time, St. Petersburg. A 3-meter long tube in which this flow of sodium was produced, and the backflow, and an external magnetic field was first applied, with the idea to switch it off later. And with the external magnetic field, they measured the voltage between here and the end. And if this voltage becomes infinitely large, we should have reached the situation of a dynamo. That's why your 1 over voltage is given in dependence on the Reynolds number. And they found such curves, and there was some hope that if they make the Reynolds number a bit larger, that it will cut this axis, and at this point should be a dynamo. But very strong oscillations occurred in this device, which at the end destroyed the device when they came close to this point. Maybe this indicated that they are really close to the dynamo situation, but they didn't really reach the dynamo in this Leningrad experiment. Yeah, and then came very unquiet times in Soviet Union, and there was, of course, the idea to repeat this experiment in a different way, but it took the time, 70 years. It took 70 years, or 60 plus epsilon, and a new experiment was then made in Riga, which it was successful. Again, this tube with this motion was used by some propeller here, and the back string, you see the dimensions, the length is almost 3 meters, and tank of the sodium, 2 motors which move the propeller. Yeah, and it was the night from November 10 to 11 in 1999 when the first experiment was done. Again with a outer with a coil which produces an external magnetic field. And okay, the apparatus worked a short time, then some sodium came out of the seals and produced a little firework, and then the system was automatically switched off. What was measured in these seconds before switching this off was this magnetic field oscillations, because a rotating magnetic field was applied, and this was measured. And it took a few days until the Riga colleagues had analyzed this, and they discovered this is the superposition of this regular oscillation, which is by the coils, as an externally applied field, and in addition a slowly growing eigenvalue of the dynamo. That means, despite of this little accident, they had the first working dynamo, working for a few seconds, close time on the Earth's surface, we assume that. After that, so this was Riga. In Karlsruhe, another experiment was prepared. The motivation was a convection pattern in a rotating sphere, which was calculated by Fritz Busse. And you see, this is an experimental arrangement which shows some similarity with this. Here are 52 such elements, each of them consisting of a central channel through which sodium is pressed by pumps and surrounded by a helical channel, and this 52 times. So it's here you see it's the dimensions, it's 70 centimeters. The radius was 85 centimeters. okay, this is just a picture. And you see that it's really a very big experiment. This was the house in which the experiment was, with 11 meters, 10 meters, again about 11 meters. This was the vessel in which this dynamo module was, which I showed you, and all this also is surrounded, the sodium tank, cooling arrangements, and so on and so on. Really a big experiment. The first idea was that this experimental arrangement is a realization of the flow pattern which was investigated by the board. This is then one of the 52 elements. And okay, I think that I should go. I should skip this. One understanding of the theory is solve the eigenvalue problem for this arrangement, or the equation which describes this arrangement. And you can do it by, for example, with the means of the mean field theory, and then you can define an alpha effect, and this is the dimension of measure of the alpha effect, and you have two loops, in fact 3 loops, of liquid sodium driven by pumps. The flows through the central channel of each of these elements and the flows through the helium channel. And you find then that you have a diagram for this C alpha, which looks like this. Central channel flows through the central channel, flows through the helical channel, and these are isolines. This corresponds to special values of C alpha. The theory says that the critical value of C alpha is in the order of 9. This is a window of what I showed you before, and this is experimental finding. Indeed, self-excitation was measured, and the curve which describes the self-excitation is similar to the theoretical predictions. Okay. Last experiment. I speak only about the successful experiments. It was done in France, in Cadarache. This abbreviation means Van Karman. It is a special type of flow in hydrodynamics. And S means sodium. They took a cylindrical vessel with rotating, counter-rotating plates here and here, which in the ideal case produce motion like this. There should be a dynamo with a magnetic field, which is force, call it theory, not symmetric with respect to this axis. Okay, this experiment was carried out the first time with a 50-liter vessel and with motors of, I think, 75 kilowatt driving this case, and no self-excitation was observed. Then a new against the predictions of the theory, but the reason for not observing a self-excitation where presumably secondary flows which are produced here. So just in this plane, strong turbulence production occurs, and okay. So they repeated the experiment with a bigger volume, 150 liters of sodium, and with stronger motors, and again nothing happened in the sense of self-excitation. A lot of calculations were made, and then they tried to modify the boundary conditions of the theory. The boundary conditions at these plates, and they replace the stainless steel plates, which are non-magnetic, by iron plates, which are magnetic. And suddenly self-excitation occurs. It is not because the permeability of the fluid has changed, only a change of the boundary conditions. Only the rigid parts are permeable materials. There's still now some discussion what really is the reason of this effect is. In any case, there is an effect observed. Okay. There are more experiments under preparation, but I did not speak about them. I will come to the end. I hope I have given you some insight in dynamo theory and principles. Thank you.
Thank you very much. In view of the time, maybe a few short questions and people can move this way.
What is the difference between paper Steinbeck and Krauser in 1967 and the paper by Eugene Parker in 1955, I mean Parker's dynamo waves?
Naja, Krause, Steinbeck, Krause, hates the alpha effect. Parker didn't give a strong derivation of the alpha effect. It was a more or less heuristic picture. I think this is a difference.
But solution in the form of dynamo waves is obtained in both papers.
Yeah.
Questions?
I really think it's wonderful you succeeded in reproducing the butterfly diagram using your dynamo theory and model. And I'd like to ask I'd like to listen to your comment on alpha coefficient. As you wrote in your book, alpha coefficient in general depend on turbulence field. But most, in my impression, most alpha model applied to astrophysics field often treat alpha coefficient as a parameter or constant. So I'd like to know your comment on this situation.
I must confess that I didn't completely understand it.
Oh, sorry. Sorry, be patient with my English. So, as you wrote, alpha coefficient itself depends on the property of turbulence.
Yeah.
Property of turbulence. That means it may alter depending on the geometry or boundary conditions. It may depend on location and time.
Yeah.
In general. But most application to the astrophysics field, alpha is sometimes considered as a parameter or constant, adjustable constant. So, I'd like to... No?
I don't think
Yeah.
so. No, you can... firstly, you mentioned boundary conditions. I think you always assume most discussions about alpha assumes that you are far away from the boundaries, that there's no influence of the boundary conditions. And then, depending on the dependence of the turbulence on space coordinates or time coordinates, also alpha effect or alpha coefficients may depend on space. Simplest example I showed you, alpha changes sign if you go from the north to the south. Yeah.
So, okay. So I misunderstood the situation. Okay, thanks.
Okay, I think this is a good time to end. I'm sure